Welcome back to Part 10. In our previous section, we switched over to the item toolkit interface to put our reliability theory into direct engineering practice. We fully configured our safety parameters using the failure model library, established our dormant standby inspection intervals, and mapped out a dedicated, standalone rate model for our external power supply grid. Now that our basic events are completely quantified, we have arrived at the final, critical stage of our safety study, executing the calculation engine and extracting the final risk metrics. In this section, we will return to the presentation slides to comprehensively evaluate all the quantitative data we have retrieved from the fault tree model. Our focus in this section will be entirely on identifying and analyzing our system's cut sets. We will break down exactly how the software identifies the unique combinations of component failures that can trigger a top-level system hazard, and we will discuss how to interpret these combinations to evaluate the structural vulnerability of our design. Let's dive right into our baseline findings. Before we look at the software output, let's establish exactly what a cut set is. In systems reliability modeling, a cut set is any group of basic events, which in our case are component faults or human errors, that, if they occur together, will guarantee that the top event happens. If you trace the logic gates from the bottom of our reactor vessel tree all the way up through the intermediate gates to the catastrophic G-explosion top event, a cut set represents one unbroken, complete pathway to failure. It is the specific scenario of events that breaches our defense in depth. When we evaluate the output of our fault tree, it is important to remember that the total risk associated with a system is mathematically computed as the sum of many different combinations of events. These combinations are the specific failure pathways, the cut sets we discussed, that would ultimately bring the system into an undesirable state, such as our reactor vessel explosion. Within these pathways, the individual component failures that lead to the top event can be thought of as the direct contributors to the overall risk of the system. Every physical valve failure, sensor fault, or operational error carries a specific weight in the final calculation. Once we generate these results, we can start asking critical engineering questions to actively manage our system safety. For example, which specific components or risk scenarios contribute the most to the overall system risk? And if we were to invest resources into system upgrades, to which components' reliability is the total risk most sensitive? Answering these exact questions is the primary goal of our quantitative evaluation. To expand on that, let's define what we mean when we talk about a risk scenario within our results. It is the exact sequence of hardware faults or human errors that successfully bypasses our layers of defense. Depending on the specific analysis methodology you are using within the item toolkit, these scenarios can be described and visualized in a few different forms. For instance, if you are performing an inductive, bottom-up analysis, a scenario might be represented as a specific path through an event tree or as a chain of events within an event sequence diagram. However, because we are utilizing deductive fault tree analysis for our reactor vessel, our scenarios are represented as cut sets, which are the specific combinations of basic events required to trigger our top-level explosion hazard. Once the calculation engine identifies every possible scenario, it ranks them for significance. By automatically sorting these cut sets according to their calculated probabilities, the software provides us with a prioritized list. This ranking is crucial, as it directs our engineering focus straight to the most mathematically significant vulnerabilities, showing us exactly which scenarios are most likely to occur. Now, we need to make a critical distinction between a standard cut set and a minimal cut set. While a normal cut set is any combination of events that triggers our top-level hazard, a minimal cut set represents the absolute smallest, irreducible combination of those events. The defining rule here is simple. If you remove even one single basic event from a minimal cut set, the top event will no longer occur. To find these, the calculation engine applies Boolean algebra to our fault tree logic to absorb and eliminate any redundant failure paths. By reducing our massive fault tree down to only its minimal cut sets, the item toolkit filters out the noise. It provides us with a clean, mathematically precise list of our reactor vessel's true structural vulnerabilities, highlighting the exact, essential failure chains that we must defend against. Let's look at exactly how the calculation engine identifies these cut sets. It does this by obtaining the minimal cut sets using Boolean algebra techniques. To understand the math, we represent the gates in our fault tree with their equivalent Boolean expressions. The Boolean variables in these expressions represent the specific gates and basic events in our fault tree. Let's walk through the table on the screen. First, for an AND gate with an output G and inputs X and Y, the relationship is written as G equals X times Y. Next, for an OR gate with those same inputs, the relationship is expressed using addition, written as G equals X plus Y. Finally, we have a majority vote gate, specifically a 2 out of 3 vote in this example with inputs X, Y, and Z. The software translates this by finding all the necessary combinations that satisfy the vote, resulting in the expression G equals X times Y plus X times Z plus Y times Z. By breaking down every gate into these fundamental equations, the calculation engine can algebraically expand and reduce the entire system down to its minimal cut sets. To finish, let's look at the specific mathematical rules the software uses to simplify these expanded equations and extract the true minimal cut sets. As you can see in the table, the calculation engine applies standard Boolean algebra laws, like the commutative, associative, and distributive laws, to structure the fault tree logic. But the true minimizing power comes from the simplification rules, specifically the idempotent and absorption laws. The idempotent laws state that X plus X equals X and X times X equals X. In engineering terms, this just means that if the exact same component failure appears multiple times within a single failure pathway, the software mathematically condenses it so we only count it once. However, the most critical rule for risk analysis, highlighted here in the red box, is the absorption law. This law states that X plus X times Y equals X. Let's look at a practical example of how this works in our software. First, we define our intermediate gates. Gate G1 is an OR gate with inputs A and B, which translates to G1 equals A plus B. Gate G2 is a 2 out of 3 majority vote gate with inputs A, C, and D. Just like we saw in the previous slide, this expands to G2 equals A times C plus A times D plus C times D. Our top gate is an OR gate that combines G1 and G2. When we substitute our intermediate equations into the top level, we get a long, unsimplified raw equation. Top equals A plus B plus A times C plus A times D plus C times D. This is where the absorption law comes in. If we look closely at this long equation, we see the single event A, which came from G1, sitting alongside the larger combinations A times C and A times D, which came from G2. According to the absorption rule, because the failure of component A alone is sufficient to trigger the top event, the operational states of C and D in those longer scenarios are completely irrelevant. The smaller cut set completely absorbs the larger sets A times C and A times D. By mathematically eliminating those redundant, non-minimal scenarios, the calculation engine reduces our massive raw equation down to the final line. Top equals A plus B plus C times D. This tells us that our system has exactly 3 minimal cut sets: component A failing alone, component B failing alone, or components C and D failing together. By applying these rules, the item toolkit filters out the noise and leaves you with only the most fundamental failure paths. That brings us to the end of our theoretical review of cut sets and Boolean reduction. We have established exactly what minimal cut sets are and how the calculation engine mathematically isolates the most critical failure pathways in a system. Now, it is time to see this process in action. In our next section, we will transition back into the item toolkit interface to execute the calculations and examine the actual minimal cut sets for our reactor vessel example. We will analyze the results, rank our vulnerabilities, and determine exactly where our defense in depth is most likely to fail. Thank you for watching, and I will see you in the next part.